Hello, and data is the topic of the lecture today, and data has an interesting and long history. My name's Richard Harvey. I'm a professor here at Gresham College, an institution which dates from 1597. My post is sponsored by the Worshipful Company of Information Technologists, who are keen to promote the education and knowledge about IT. And data is one of those, I'm bitterly regretting choosing this topic. It's wildly ambitious and far too big, and I'm never going to get through it all. But one good thing about data, unlike, say, the word like algorithm, which is relatively modern, is that it actually has a long and distinguished history. And in 1597, when the college was formed, the word data was probably pretty much being used as it was now. This is one of the early citations of the word. It's a book by Sir William Batten, who was contemporaneous with Samuel Pepys. Pepys was another Gresham professor here. And, well, I should say, Batten wasn't exactly liked by Pepys, and if you're interested in seeing some of the more vituperative remarks in Pepys's diary, look up William Batten and you'll find about it. But he did know about data, and he was a navigator, and here he is using the word in the original meaning, which is a plural of datum, meaning position or location. And I think pretty much, that is the way we would use it now, and it's got generalized not to be location, but sort of digital stuff is what I'm interested in, and that's what I'm going to talk about in this lecture. So I'm going to take you through what I've called the 7 ages of data, and I want to start in sort of computer prehistory, tell you a little bit about computers, show how that influenced the way we store data, and then I'm going to bring you up to date, and we're going to look at the way data has been used by computer science over, well, let's say the last 70 years, something of that duration. So I'm going to start with a little diagram of a computer. Don't freak out if you're not used to seeing these things. This is actually quite a simple model of a computer. The box on the left, called the CPU, or central processing unit, is the thing that does the work in the computer, does the thinking, if you like. And the box on the right, I'm just going to call memory. Now, in the old days, we would have obsessed as to whether we were talking about random access memory or ROM or hard disk or tape or any of those things. Let's just call it memory. And the way a computer works is it decides whether it's going to read or write from the memory. So it sets what I've labeled the read-write line here, either up or down, depending on whether it's doing reading or writing. It then sets a binary number on a set of lines. And when we have a set of lines in a computer, we usually call them a bus. Omnibus, meaning all work, but also a bit of an analogy with a bus in that you can take things on and off it. It's a bit of a weak analogy, but anyway, it's called a bus. And in a primitive computer, there might be, say, 16 of these address lines, and we set them up to the address that we want. And then we read on the data lines, data bus, the information that comes out of it. And if we want to write, we just set the read-write line a different way, and the data that's on the data bus is read into the memory. Now, why do I mention this? A consequence of this is that in a modern computer, you're reading information from memory in these chunks called words. And if we went back to sort of early days of computing, well, not so early, but sort of 8086, Intel 8086, that's IBM PC, first IBM PC, that data bus would be 8 bits wide, and the address bus might be 16 bits wide. And that places some constrictions on the way computers can handle data. And when it's only 8 bits wide, they're quite tricky constrictions to work around, actually. Nowadays, if we take a modern processor like Ice Lake, there you go, that's the latest of the Intel 8086 line, that would have a 64-bit data bus and gives you a bit more flexibility in a 57-bit address bus. Okay, so let's just have a look at what that looks like as a sort of model for dealing with memory. And probably the operational part here of this slide is the line on the bottom. And what I've got on the bottom is these I've got these chunks of 8-bit words, and the challenge is to fit stuff into 8 bits. Now, 8 bits gives us 2 to the 8 combinations, 256 combinations. So you could represent an integer, a whole number ranging from 0 to 255, or 1 to 256 if you didn't want to represent zeros. You could probably fit all the characters in there, English characters anyway, not other languages, but English. So you can easily fit in your lowercase letters, your uppercase letters, and so on. And if you're interested in that, there's a lecture by me on text processing, which explains character mappings. But other things are clearly not going to fit. You know, we can't have computation relying on just 8 bits. So they're going to have to spread across multiple words. And that means when we do a fetch from memory, when we do that process I just described, we're going to have to read multiple words, and then we're going to have to stack them up. And then if we do addition or multiplication or something, we're going to have to swap information from those various words, and it's all going to be a bit slow and painful. So in the early days of data, there were these, computer data anyway, there were these quite troublesome mappings that had to go on from the physical world out there into the interior of the computer. And sometimes, well, certainly in the early days of computation, one wasn't insulated from that at all. It was really only until high-level languages started to come along that there was a possibility of the programmer or the user of a computer not having to worry too much about the underlying hardware of the computer. I should say, you know, we worry about it. Almost everyone has to worry about these things, but you can progressively abstract away from the bottom end, the lower level part of the computer. And I've just taken an example of quite an early language here. This is Fortran 77, and you can see, well, let's have our first bit of programming. You know, here are some declarations of various types of things in Fortran 77. If you don't know, Fortran was a language developed by IBM in the 1950s. It was designed to run on one of their early computers called an IBM 704 by a guy called John Backus. Actually, I wished I hadn't mentioned the IBM 704. It's diabolically a computer that didn't have a multiple of 8-bit words. It had 36-bit words, I think, a rather peculiar thing. Anyway, this was the bee's knees in the 1950s, and if you had a couple of hundreds of thousands of dollars to spare, then you could have one. These these data sizes here are carefully matched usually to the underlying hardware that you expect it to run on. And if you're a programmer, you can easily, well, I say easily, you can sometimes not easily find the mapping from a language to the physical hardware. Now, let's have a look at some of these data types, and I want to pick one because it's the one that we sort of encounter in every day, which is real numbers, not whole numbers, integers, but real numbers. They're things that are used to measure things or measure the mass of something or the length of something or the volume of something. Those are real numbers, decimal numbers or fractions, that sort of thing. How are they stored? Well, they're stored in a system that we call floating point. And, you know, the idea behind floating point is it enables us to handle things with very large scale variation. And, you know, the world is full of examples of this. And so here's my example of a number, 3.14159, a number that a lot of you will recognize, no doubt. And it's perfectly viable to represent that as plus 312,159 times 10 to the minus 5. And 10 to the minus 5 means move the decimal point back to the correct position, five positions back to the left, in fact. Now, just to give a bit of notation, we would usually refer to that number 10 as the base of the floating point number. The number minus 5 is called the exponent. This number here is called the mantissa, not an everyday word, but the green number is the mantissa, and then this is the sign. So the trick is to pack those words into some sort of digital form. Now, we don't need to store the base because the standard just agrees that we will use a fixed base. We're used to using base 10, of course, because we work in decimals. Computers tend to prefer powers of 2 because they're binary systems, so computers will usually use base 2. So the way that would work in IEEE 754 floating point, which is the standard that everyone uses for storing floating point, is something like this. So I've packed it into 3 binary things here. On the left-hand side is a white 0, and that's the sign bit. Then we've got the pink digits, and they're the exponent. That's -5 in binary coded decimal, I should think. And then the green is the mantissa component. And that packs neatly into something, into one of our words. Now, one of the features about floating point, although you think that's fantastic, we can represent a whole range of numbers, which we can, is, of course, that we're making some approximations. We're making approximations because the mantissa isn't as long as all that. Well, we're used to that, okay? We're also making some approximations because humans often represent things in base 10 and computers have got these in base 2, so there's a conversion error there. And we've also got the issue that as we get to very large numbers, the steps between them become progressively larger. That's the consequence of using this exponent notation. And that can cause some fascinating little challenges when it comes to doing computer arithmetic. So it's a sort of trivial thing to say that we can't represent all numbers equally in floating point, but when you look at the consequence of this, it can be quite fascinating. So if I take my number here, convert it into its binary floating point, IEEE standard floating point, and then convert it back, I end up with a slightly different number. It's different in some way down there, and if I look at the difference between that, I get an error. It's a small error, but it's there. And the issue about these small errors, they're small, but they can add up. Now, I can see you sort of, well, I can't see you, but I can sort of imagine you leaning back saying, oh, well, Richard, this is very trivial, Who cares? Computers have infinite precision or very large precision, and these things are very trivial. I'll just sort of demonstrate why it can be a problem, because it's kind of fascinating. I think that even in this age, it can be a little bit of a challenge. And here's a little cute example. So let's say I wanted to add the number 10 to the number 0.1 using, let's just assume I've got some very simple floating point computer that only has 1 digit for the mantissa. So what we would do is we would take the number 10, which I'm calling x here, and that's 1 times 10 to the 1. I've got y, which is 0.1, which is 1 times 10 to the minus 1. We add those together, it gives us 10.1. Then I have to round it, okay, which gives me 10 again. So in my simple computer here, I've got the rather alarming situation that x plus y equals x. Well, and if I add the small numbers plus the big, then I'll get the 11. So if I add 10 times 0.1, that's 1. 1 plus 10 is 11. I get the right answer. If I do it the other way round, I get 10. So big E followed by smalls, or big E smalls, if you like popular references, is notorious for giving you troublesome additions. Now you might think, this doesn't really happen in reality. Well, here's me just mucking around with Excel. And so what I've done here is I've just, you can see me typing, yeah, good. I'm going to create a column of numbers in column A that is 1,000, I think. Yeah, it's 1,000 numbers ranging between 0 and 1,000,000. So 1,000 numbers is not a lot to have in a spreadsheet. At least I don't think so. I mean, people are always sending me spreadsheets at university with 1,000 something on it. Perhaps I'm sure they shouldn't, but they do. And then in column B, I'm going to sort those numbers from smallest to largest. And then in column C, I'm going to sort them from the other way round, from highest to lowest. And on the right-hand side, I've written a little sum, which is either summing the output from column A, or column B, or column C. And what you'd expect, I think, what you'd hope of a very, very well-known program like Excel, Excel is a sort of programming language, is that you would get the same answer. And how are we getting on? Well, it does look like we get the same answer until I look at the difference between column B and column C, and I can see a difference. Now, I actually don't know if how Excel does its summations. There is a way of getting around this. It's called compensated summation, or the Kahan algorithm. There are quite a few algorithms for solving this. Basically, you sort them, or you do them pairwise, matching them off against each other. Certain languages do them, do these compensated sums. Python, for example, if you use fsum in Python, it does a compensated sum. Or Julia, if you've come across that. It's a newish sort of Python-like languages, does pairwise summation. But lots of them don't. So BLAS, for example, the basic linear algebra subroutines, which form the basis of a lot of computation, simply doesn't do this. In fact, doesn't tell you what it does. I don't know if Excel does it. You can, if you're an enthusiast online, go and find out. I didn't have time to check. So this was the first age of data. And what I've just shown is you might be wanting to dismiss this sort of irritating, sort of trying to munge the data into the words we've got available business. All in computer prehistory doesn't really happen. Does happen, okay? It's happening in Excel, and it needs care. And that care is called numerical analysis. Okay, numerical analysts are still out there, and they're still looking at problems like this, and they can bite you. They've certainly bitten me in the past, numerical analysis problems. But that was the first age of data, where we were fitting the data into the computer structures. The second age of computer data is more sort of imaginative. And what we started to do as we moved towards high-level languages was we started to be able to use data to help us solve problems. So some of those data structures, as they are called, are incredibly common in computer science. And the simplest one I could think of is an array. An array is it's a list of numbers in memory, and generally speaking, we store the head of the address, and if we know it contains, say, long integers, at 32 bits, then we increment our address by 32 bits each time, and that takes us to the next one in the array. And because computers can do integer addition very quickly, you can zoom along an array very effectively. Arrays are beautiful for storing scientific data. And, well, if you've used Excel, you're familiar with an array. You know, a row or a column is basically an array. And if you've used Excel, you know the problem, which is when you run out of the array, you have to create more space. Now, Excel does that for you automatically just by scrolling down the page. What's happening underneath that is more space is being found in the computer, and you can hear it sort of chattering away while it does that. There are things called strings, which are just arrays of character data. They're used commonly in input-output and reading human letter. But you can do more exciting ideas. More exciting ideas come to the fore in most modern languages, and that's mixed data types, as we would call, not just arrays of char or arrays of integer or so on, but structures that might represent something that means something to people. So I've got an example here of a patient record, and it seems to consist of a string, which I've called give name, a string which is called family name, integer for age, and a real, which is their height. And if we got out our microscope and looked at how this was stored in memory, then we would see contiguous blocks of memory assigned to these various bits of data. So here's a particular record. I've got the patient's given name at the front, which is Sam, and then his family name, which is Peeps, his age, which is 50, and his height. Well, I've abused the length a bit here because I didn't want it to go across the screen. I've just used 3 8-bit integers to hold his height. And these little arrows here, pointing to where these elements can be found, these are called pointers, okay? And pointers are very common in computer science. We use them to index into data structures. So when you hear a computer scientist talk about pointer arithmetic, what they're talking about is the ways of handling these addresses. And the management of memory, which I'm not going to talk about in this lecture, is also a fascinating topic. But it doesn't always go as planned. And when it doesn't go as planned, you end up with data structures in the wrong parts of memory and potentially catastrophic things. Now, standard sort of computer science repertoire introduces a lot of these data structures. And some of them are so standard, they get given their own names. I've talked about one, which is an array. And the problem with an array, as I said, is it's not dynamic. It's not easy to adjust it to match the amount of data coming in. So one of the alternatives to an array I've drawn out here, and it's called a linked list. And a linked list is a completely flexible structure. It's very easy to add data to it because each element, I don't do computation to scan along the element. I just look up the address of the next element. So the first number here, 3, is stored next to an address which points to the head of the next element in the list, which is 1, next to an address which points to the next list, and so on and so on. Hence the same linked list. Links are these little arrows that connect one thing to the other. Now, if you look at that stored in memory, you might assume that they're contiguous. That's not the case at all. Their contiguity, if that is a word, depends entirely on the order, the timing in which you started to request these things from the computer operating system. So in this case, these numbers running along the top here are addresses, and so we can see the first element here is on the left of the list. It's 3, and its first address is 15690, which is some way down the list. So if I put the pointers on for you for this array, you can see that the first element goes to the right to a higher address, and then the second element points back to a lower address, and so on. And it's a real old muddle. Now, this arrangement, when you've got memory holes here, is called fragmentation. And I don't know if you remember hard disks. You might even have a computer which has a hard disk. They're not very common now. But hard disks used to use this linked list structure in order to store blocks of data. Again, the problem was that hard disks had fixed chunks. Your data wouldn't, your file, your WordPerfect file wouldn't fit into that chunk, so a bit had to go here, a bit had to go here, and you had all of these links. And eventually, following those links got a bit slow, and you would do something called defrag the disk. And it was a problem on hard disks. If you've got a solid-state drive, and everyone's got one of those now, I suppose, it's exactly the opposite problem, actually, because solid-state drives wear out. If you keep reading and writing to the same part of the memory, they have a restricted number of read-write cycles. So solid-state drives deliberately spread the data out, so fragmentation is good on a solid-state data structure. Well, imagine a linked list, but instead of having one element that each pointer pointed to, you could have 2. Well, that is also a very common data structure in computer science, and it's called a tree. Looks a bit like this, symbolically. Each one of these ampersands represents an address pointing to somewhere, and when I've got a 0 in that, it's not pointing to anyone. Tree is a very common data structure in computer science and appears all over the place. Just a word of warning, there are 2 sorts of trees. There are trees spelt T-R-E-E, and there are also trees spelt T-R-I-E, which some people pronounce tries. A trie is also a tree. It's a tree used for a particular purpose. I haven't got time in this lecture to talk about tries, which should be pronounced trees. But go to the web and have a look up trees, the other sorts of trees. They're quite fun things to do. But I have got time to briefly explain how data structures can lead to new insights on algorithms and problems that we have in the real world. So I'd like to take a little example, and the example I'd like to do is a segue into an important part of this lecture, which is to talk about databases. Okay? So let's imagine a simple database, and a simple database is just an array of stuff. Okay, so this is my array of numbers in this case. Now, I'm just going to assume we've got these numbers here, but typically there would be other stuff indexed by those numbers as well. But let's just assume we're trying to deal with these numbers. And what I've done here is I've got this array on the right-hand side containing the numbers. Notice it's a typical array, and it's got 3 empty elements. There are 7, instead of, it was a bit boring having to write 7 billion on a slide, which is sort of typical size of a database that we might be interested in. So I wrote 7 because Newton thought it was a magic number. There are 3 empty spaces on the end of this array. And so I've marked the end of the array with a pointer. Remember I talked about those pointers, their addresses, and this one's called end. So here's my number, x. And the 3 things I would like to be able to do with a database is to either search for x, look down the list and find the value x or not. Say, is it there or not? And if it is, where is it? I'd like to be able to insert x into my database, and I'd like to be able to delete a particular value. So search, well, how long will search take, you might ask? Well, it's going to take n operations, isn't it? Because worst case is I keep going down here and I don't find x, so it's not there. So if the list is 7, it will take me 7 operations. If it's 7 million, it's going to take me 7 million operations. So we would refer to that as an order n operation. Now, what about insertion? Well, insertion is dead quick. We just bang, it goes on the end. Because we've got that pointer on the end, it's really efficient. Now, what about deletion? Okay, well, deletion is a bit like search in the sense I've got to find the element I want to delete, I've got to strike it out, and then I have to move up the other ones. So I hope you can see that if I just start with a standard array, I've got a process here. A database has these 3 standard processes you want to do on it, search, insert, or delete. That the search is order n. Insertion is really quick with this data structure, but deletion is also order n. Now, word of warning. If you watch my previous lecture, you will probably be aware of the Cobham-Edmonds thesis. And the Cobham-Edmonds thesis is used by people who talk about algorithms, and it basically says if it's polynomial in n, less than polynomial in n, it's a trivial problem, let's forget about it. Now, that is far from the truth. That is true enough when you're doing lots of complexity thought about how really difficult some things are. But it's not true at all when it comes to reality. And databases are all about detail. People who work in databases really have to confront a lot of, very demanding business customers every day. And as I will show in a moment, order n might be problematic for a large database. Okay, so could we improve on this? Well, how about sorting the array? Okay, well, let's try that. So what we could do is quickly sort the array, and I say quickly because this is not a quick task if you've got a very big array, and instead of storing the endpoint, I'm going to store the middle point or the median value. That's the middle of a sorted list. In comes my variable x, and I want to do search first of all. So all I do first of all is I say, well, is this in the top half or the bottom half? And that's easy because is it less than or more than the median? Well, if it's in the top half, then the problem is halved in size. Right, well, I'll do it all again. And the problem halves in size until I've got to the right point. Okay, that's a divide and conquer or recursive type approach to algorithm development there. And so because I've got this progressive halving, my search complexity goes down from n to something considerably less than that. Now, what about insertion? Okay, well, insertion is now a bit more complicated, isn't it? Because I've got to put it in the right place. So I've got my variable x. I'm going to need to find the right place, pop it in, and move everything else down there. So that is potentially worse. So if I use a sorted array, my search complexity goes down to log 2n, which is great. That's an improvement. But insertion has got worse, and deletion is still at order n. Okay, not quite there yet. Let's have a look at a third alternative. Before I do that, let me just explain the issue, because I perhaps haven't made this super crystal clear. let's imagine I've got a database that holds the population of India, okay? Well, it sounds a bit bizarre, but there is such a database. And if you look at my lecture on biometrics, I talk about one that's called the Aadhaar system, which is the identity database for the population of India. So 1.4 times 10 to the 9 people in India. But it's easy to get up to those numbers when you're dealing with scientific or commercial data, no question about it. And let's assume it takes me a microsecond to do those comparisons. So how long will it take me to do a search? Search is typically one of the things we worry about, because there's a user there saying, find me this person in India, types in their name, hits return. Well, how quickly do you want the answer? Like that, right? You don't want to wait. So how long is it going to take me? Well, I just multiply the two things together. 1 times 10 to the minus 6, 1 microsecond, times 1.5 times 10 to the 9, 1,400 seconds. 1,400 seconds! I mean, if you design a database that takes 1,400 seconds to do a search, I don't know what to say. You haven't actually designed anything. You are part of the problem. You are not part of the solution. So one of the structures that might help you with that is called a binary search tree, and I've illustrated it here. It's the same numbers, except now they're ordered, with the median is up the top of this tree, and everything to the left of a particular number is smaller than it, and everything to the right of that number is larger than it. So you can easily see how a search just takes you down the tree, and just like the sorted array is going to turn out to be much quicker, because we don't have to search through every item. We only have to search down the branches of each tree, and there's far fewer depth to the tree than there is elements in the branch. Okay. So just a reminder, sorted array complexity. Well, this is what we have with our sorted array complexity. Now, let's just have a look at this log 2n with my India, population of India example. Okay, still times 1 times 10 to the 3, but now it's log 2, 1.4 times 10 to the 9, 30 microseconds. Wow. Right? 1,400 seconds with the wrong data structure, the obvious data structure, 30 microseconds with a sorted array. But the sorted array has these very nasty insertion and deletion costs. Well, maybe you could live with them, but they're still uncomfortable. Now, what about my lovely new structure here? Well, everything in the new structure has the nice complexity. So when we're working with the binary search, when we're working with the old data structure, 1,400 seconds. When we're working with the new data structure, we're down to 30 microseconds. We're not storing too much extra data. We're storing some, because we have to store these addresses, but it's not horrendous. And this new structure is called a binary search tree. Now, these binary search trees are, they're a standard part of, well, congratulations, if you like. You now understand Comp 101 data structures. This is one of the sort of standard questions in computer science undergraduate syllabi. How do you build it? There's quite a few algorithms for building these things. I'm just showing here a nice little illustration of the web using a particular algorithm known as the AVL algorithm, named after the inventors of the algorithm. And the AVL algorithm does two things. One is it builds it on the fly. That's important. It means we don't have to do this sort of array business of guessing how much of an array we need and then filling it up, and then when we overrun it, going, oh God, quick, get me some more data, go through all of that. We build it as we go, so that's nice. And it's called a self-balancing algorithm. Is it obvious? Perhaps it's not obvious, but if you can keep these trees balanced so they have exactly the same number of, same depth down each one of the branches, it will be as quick and efficient as possible. So what the AVL algorithm is builds dynamically on the fly. If you'd like to see it working, just Google AVL BSG tree example, and something delightful like this will happen. This is an example from, I can't remember where I got it from, but anyway, I'm sure you'll find it. Right, okay, so that's our AVL tree. Now, do you see we've moved into a new sort of type of data structure here? They've evolved from being, data structures were annoying things that we had to deal with because of the limitations of computers, to powerful things that we can use to help us design clever algorithms to solve problems. And if you look at good algorithm designers, very often they'll start by thinking about the data structure. Actually, on YouTube, there's a wonderful set of videos about how to get a job at Google. Google is famous for asking difficult questions at its interviews, by which I mean, what was I going to be rude about Google now? They really are difficult questions, and they've got quite challenging questions. And even professors of computer science go, that's an interesting question, I'll have to think about that. So you can see that when you watch people solve these questions, often competitive programmers solve these questions very often for a laugh, they'll often start not with what you might think of the procedure for solving it, but they'll say, well, I think this is best represented as a tree, or a trie, or a graph, or a bipartite graph. So they start thinking about data structures before they're thinking about solutions. However, this was a beautiful segue, I thought, into databases. And I suppose everyone has a sort of simple concept of what a database is. And what a lot of people think of as a database, a mailing list that they've got an Excel or something like that, is what computer scientists would call a flat file, usually. Flat files don't need to just be in human-readable text, although they often are. They're just files where the records, as we would call it, and a record is a line across the rectangular bit of information, are all stored contiguously. So I've made one up here. This is a sort of example of the database that we might keep at Barnard's Inn about Gresham lectures. Well, there are 2,000 Gresham lectures on YouTube, and there are certainly more lectures being given than recorded, but that's the number on YouTube. And they're growing, 130 a year. So it's not unreasonable that you would keep a list a bit like this. And don't worry if you can't see the elements. I've got a title. Here's my title, Data, the Past, the Present, and the Future. And underneath that is Chris Whitty's title, The Changing Geography of Ill Health. And it's got the date, the time, the lecturer who's giving it, and what we used to construct the slides, who did the tech support, who's doing the publicity, how long the transcripts are. By the way, all Gresham lectures have a transcript. Do have a look at it. They're quite entertaining. In my case, they bear no relation to what I said, so you get the lecture twice, if you like. The transcript is the lecture I wished I'd given, but it's full of jokes and rude remarks about people, whereas this lecture is more restrained. And the series and so on. Now, no problem. So we've got records. A single record runs across this way, and down these columns are what database gurus call attributes. Now, one of the issues with database designers are not only worried about efficiency, they're also worried about keeping data integrity and trying to keep it consistent. So one of the nightmare situations, for example, is changes. So let's imagine something a bit bizarre. Let's say I was worried about my citations. Not enough people are listening to my lectures and reading my papers. I've got a brilliant idea. I will change my name by deed poll to Chris Whitty. Chris Whitty is a Gresham professor. He's also the government's chief medical officer in the United Kingdom, so he gets a lot of hits. So I'll change my name to Chris Whitty, and then everyone will love my lectures. Well, I try this for a few months, and then I change. So that's easy. The person who maintains this, they just do a search in Excel for Richard Harvey, they replace it with Chris Whitty, and off they go. And then, it doesn't work. So then I'm changing my name back to Richard Harvey. Now, how do we deal with that? We can't do a search for Chris Whitty and replace Chris Whitty with Richard Harvey. You have to go through every single lecture and check whether it's consistent. Now, that sort of update process is very common in databases. You change your address and it ends up... And you see the errors of this in everyday life, don't you? You're getting mail bombed with ridiculous mailings about embarrassing itching. I had any embarrassing itching, but they've got you mixed up with someone else and the addresses have got confused and it's horrendous. So these sorts of problems are very common in database fiends. So... naming problems are common enough. When we say Richard Harvey, do we think of the very intelligent and brilliant computer scientist? He's the one in the middle there. Or do we think of, the famous composer Richard Harvey, or do we just go with the surname, which is now spelled Harvey, H-I-H-R-V-Y, who's a popular singer in the United Kingdom. And so all of these problems are quite concerning. And these sort of issues started to come up as people were designing databases, largely in the 60s and 70s. So the realization was that it would be a good idea, even if it might not be super efficient to do so, it might be more efficient in terms of human error, to split these things up into standard forms. So they're called normal forms. And they're a bit dull, actually. You can go through quite a lot of these normal forms. There are 6 of these wretched things. I'll just show you how one of them works. So what I would do here, my first objection to this database is that we've got a line here where tech support contains 2 people, Richard and James. And that makes querying a little bit awkward. So in first normal form, we try and get rid of that. And the 2 things we do in these ideas is we add a key to the data. So instead of relying upon, something that we believe is unique, which might be the title and the name of a lecturer, or when you start thinking about these things, they're not as unique as you might imagine. Remember, let's take an example. If you said, what are popular subjects for lectures at Gresham College? Black holes, okay? Or Tudors, right? So if I'm going to give the ultimate, or the Nazis, so if I'm going to give a lecture on Nazi Tudor black holes or something, there'll be a lot of those. So instead of that, we'll have a unique key. And that's in my little top table, has a unique key. And I'm going to have a second table, which has a relation to that first table, and that lists the tech support and the associated key. Right? Relation equals relational database. So if you've heard the phrase relational database, it's developed by a guy called Ted Codd in the 1970s, he was actually I don't know where he was. I think he was another IBMer actually, but I might be doing him injustice. So if you've heard the phrase relational database, that's what it means, multiple tables with relations between them. RDBMS, relational database management system. It's nothing more fancy than that. Nowadays, every database is a relational database. This is a good time to talk a little bit about the history of databases, actually, because they've really driven an incredible number of business processes, and in fact, societal changes have been driven by databases. They're a sort of hidden hero of the IT world, actually, the database. It was really about the 60s when people started to have a problem with computer data. And my photograph here, which is taken from the Library of Congress archive, taken in 1941, and what it shows is people dealing with booking a flight. And I don't know if you've ever given this much thought, but the prospect of booking a flight full using bits of paper is a fairly gruesome one, I think, and that's what's happening here. The gentleman is stacking bits of paper with people's names on into these slots, and when they're full, the aircraft is full, and that's how they used to do it. There was an advanced system used by American Airlines, who had a big carousel, and if you wanted to change your flight or through book, you had to book the hub from where the flight departed. So you had all of these conversations with individual people, and if you wanted to move your flight from Pan American to American, it was multiple phone calls. Horrendous situation. Okay, well, this was a famous case, actually, and it's become so famous, the system that solved this, that many apocryphal stories have been built up about Sabre, which was the first flight booking system. It was developed by American Airlines in partnership with IBM, later produced this spin-off company called Sabre, which still exists. Actually, it's fascinating commercial history. I mean, at the time, IBM just wanted to sell software, so they dramatically underpriced this system, and it was seen as a big failure at the time because obviously big systems cost a lot of time, and they had lots of problems with data structures. Querying was pretty slow, and there were problems mapping to the hardware, and all of these things which I've been talking about up to this point weren't really sorted out. But they got there, and Sabre is now, still a market leader, and particularly in the US. If you're booking, you're probably booking on a Sabre system. So the 60s were, and the theoretical work that I've sort of talked about a little bit was preceded by these practical systems in the 60s. In the 70s, we had these issues which were all brought out in relational databases. The 80s was really about developing those databases using a language called SQL. In the 1990s, we moved to the internet age, and I'm sure this is obvious to you, but when somebody talks about a website, it's a database, all right? So unless it's a website of trivial complexity, if it's a website that's selling you anything, if you've gone to my blog, prof-richard.org, for example, which is my website, I just do that on Wix, which is a commercial provider, and they use a database to serve me up pages, and they use the editor as a database, and the way it's served is a database. If you're using Amazon, you type in Thomas Gresham into Amazon, you are issuing a query in the URL of the database to the Amazon database. It says, please return everything that contains the words Thomas and Gresham in it, and then order them by some bizarre, well, usually I assume it's whatever makes the most money for Amazon is the ordering, and that's how you get the web page. The database is constructing that web page for you on the fly. So that was the era of commerce. And I'll talk about these other things as we get to them. Right, SQL. Okay, well, I'm sure if you've heard people talk about databases, they've talked about SQL, structured query language. Now, okay, top tip. If you're really into SQL, you don't call it SQL. You call it SQL, okay, SQL. And that's because the first generation of this was called SQL, and it's just stuck, okay? So cognoscenti, they call it SQL. This is what it looks like on the right here. And it's a SQL database is all divided into columns, and instead of having to sort of write loops to go down these columns and say, is this equal to this, you can do it in a single command. Very powerful, as long as the database is stored effectively. And SQL has some interesting properties. I mean, the first commercial interest really, first commercially interesting thing to come out of SQL was Oracle. Okay, I don't know if you've heard of the company called Oracle. They're enormous. I mean, they're the largest internet company you've never heard of. I mean, they're run by a fascinating and very colourful man who I better not talk about. But do look up the history of Oracle. It's a fascinating American company. SQL is now standardised, and I'll talk about this a little bit later, but there are some recurring themes that will come out through these lectures, and standardization is one of the recurring themes. So SQL was developed in the early 70s, 1974, I think was the first version of it. It was standardized in 1986. That's a lifetime in computer science terms. It's absolutely huge. What happened? Oh, well, standards committees take a long time to debate it, and then there's this sort of standard and that sort of standard. And in that time, people build a customer base and they build loyalty. So that's a big problem. It means that for various reasons, languages are usually not on standard, and that's one of them. Secondly, SQL has it's a big standard. So compliance is tricky. Thirdly, databases have a long lifetime. So companies are very reluctant or have been very reluctant to move databases from one storage standard to another for very good reasons. That's their business. A lot of companies. What is Amazon? Well, it's just a database and some warehouses. They're very, very cautious about dealing with their legacy software. And the other reason is lock-in, of course. Lock-in is a particular term related to computing, and it's a wonderful bit of business. Lock-in is the effect that you've always worked on Microsoft Word. You're not going to change to OpenOffice, even though OpenOffice appears to have all of the same features. You don't know how to use it. It's a hassle to change, and you're worried that they're not interoperable. So lock-in is a very important factor. So SQL was the 1980s innovation that was so important for data. Another thing that came out of database analysis that has become much more useful, and I should say, I'm really picking and choosing here. There's probably 100 things that have come out of databases that are incredibly important for the way we think. I picked this one because this is a bit of philosophy. It's called an entity relationship diagram. So I don't know if you're familiar with philosophy, but there's a branch of philosophy called ontology, which is how things relate to other things. And there are people in computer science who work on ontologies. And ERDs are a way of representing ontologies. So how this diagram should be read is that there is an entity here called a lecturer, and a lecturer gives a lecture. That's what the line might represent. Well, I haven't written gives on the line, but you would do normally if there was any confusion. The multiple little arrows, the thing that look a bit like a shuttlecock or an antenna, that indicates that there could be multiple lecturers giving one lecture, or there could be multiple lectures given by one lecturer. And then there is a thing called a professor, Gresham professor in this case, particular professor. They have a fixed period, and there's only a few of them, 9, I think. And they are a type of lecturer. Not all lecturers at Gresham College are professors, but all professors are lecturers. Okay. And these entity relationship diagrams can either be used at a sort of conceptual level, like this, but the beautiful thing is that with a bit of care, you can map them into a logical level, or what we would call a physical over on the right-hand side. And what's happened over on the right-hand side is I replaced some of these conceptual ideas, like first name has become a varchar of 200 characters. I made a decision here that no lecturer in Gresham College can have a first name longer than 200 characters. By the way, these sorts of decisions can bite you, and they're not trivial decisions, and they can cause a lot of problems. So ERDs were a sort of gift from the database community to the world, and I sort of commend them to you. There are plenty of these other tools. I'll try and talk about some of them in other lectures. Actually, graphical tools for understanding the world. Another one that sort of cropped up, perhaps not directly from databases, but certainly influenced by the internet age, was XML. So I said that as we move towards the internet age, databases became the driving engines of the web. And the web introduced us to a new sort of language called HTML, hypertext markup language. It's not a language that tells somebody how a computer to do something. It's a language that tells you how to write something, how to process something. So it's a language that explains the meaning of various things. And XML has become incredibly, which is a variant of, it stands for extensible markup language, is a sort of markup language a bit like HTML. HTML doesn't describe text. XML doesn't describe text, though. It describes data, or in fact anything. And if you're curious, you use it every day. And I'm sure you're probably not aware of this, but you're writing XML every day, and I can show you that. Here's an example of a PowerPoint slide. This is my generic this century PowerPoint slide. So it's got the phrases elephant in the room, low-hanging fruit, and hit out of the ballpark on it, always found in all good corporate presentations, and a big blue square, which I probably should, nowadays we would make it a cloud, because everything has to be a cloud. Right, and over on this is a bit of PowerPoint. Over on the right-hand side is the XML that's sitting inside your PowerPoint. And if you want to see this yourself, get your PPT file, unzip it, and you'll get this great big nest of directories, and in there you'll get something called XML, which you can open and read. And if we have a look at it, then the first thing you will notice, sorry, this is a bit small, but you don't need to read it, there are some things called schema. And schema, or document type definitions, are human readable descriptions of what sort of data we would expect to find in this file. So it might say this file contains a rectangular region which has a color and it has some coordinates. In fact, this PowerPoint does allow that, and that is one of the standard shapes you can draw in PowerPoint. So the schema describes that. And you can read the schema and work out what is acceptable and what is not acceptable in the data. And if we scroll through this, I don't know if you can see this, but you will see the green bit here was the descriptors for the text, and the pink bit here is the descriptors for the rectangle, and the white bit is the descriptors for the bit at the end. And if you look closely, you can see there is an element here called elephant in the room, which is this element that's being rendered here over on the left-hand side. Well, this is really powerful because you can use XML to describe data. It's data about data, or metadata. And when we were all working on MPEG 7, which was the retrieval standard of a few years ago, it was very common for people to say, perhaps rather sententiously, I think, oh, the metadata is more valuable than the data. It's not true, but I mean, it sort of makes you think a bit, doesn't it? Data without metadata is meaningless, isn't it? Because nobody knows what it means. So the metadata certainly has value. Metadata without data, probably also meaningless. The two go together. A very important, but it was a very important sort of thought point in the history of computer data, because the idea that you could keep with the data its own description is a powerful one, and anyone who's sort of rifled through shoeboxes of tapes trying to find stuff can appreciate that, I'm sure. One thing that I was less impressed with was big data, okay? And, oh, God, we had decades, we had years of this when people would waffle on about, big data and how it was terribly important. And, whilst I sort of appreciate the idea here, so big data was started by McKinsey Global Institute. McKinsey is a very well-known consulting company, if you don't know it. If you want a quote about McKinsey, I've got one here, which was from Forbes magazine. It said, McKinsey is the most well-known, most secretive, most high-priced, most prestigious, most consistently successful, most envied, most trusted, most disliked management consultancy firm on earth. So when they write something about big data and how if you're a manager, you better jolly well understand it or you're all going to go bust, obviously people take notice. The problem with big data is that nobody has yet defined what we mean by big. So big data is a sort of waffle word when you say, well, big data, there's lots of it, that's high volume. It's got high velocity, it means it's coming at you quickly. And it's got a lot of variety. So what they meant by variety is, it can come from all sorts of places that you haven't been expecting. I think a better term really is data science. Okay? And data science really means using the techniques of artificial intelligence plus skilled data management and metadata to convert the sort of torrent of data into insight. Data by itself is not interesting to people running organizations. What's interesting to them are conclusions and insight, okay? And that's what data science is all about. So if you want to annoy somebody when they're using big data, what I should say to them is, the first question you should ask after they've been waffling on for a bit about big data is, what do you mean by big? Now, this will have the effect of you sort of slapping a carcass of a wet fish into the middle of a rather tasteful dining party. It would be regarded as pretty bad manners, but I don't think you'll get an answer. So we're currently in this age of data science, and if you want a beautiful example of data science, then I gave a lecture last year on the digital university, and there was a really nice example in there that I refer to in the transcript of getting inference out of unstructured data. So that brings us full circle to the 7 ages of data, as I've called it. And I started with flat files, which were these, the data as it occurs, Darwin's notebooks, that sort of thing. Then I talked about how data had to be forced into a format for computers, that's data for computers. And then I showed how with a little bit of imagination, you can use data structures to help you construct algorithms. So that was the age of the data for algorithms. And I should say all of these things we're still in these ages, they don't go away. Then I talked about databases, and the construction of databases was a story of detail, really, and a huge, huge commercial importance. And I could have put other things in here, I could have put the internet age and all those things, because e-commerce and the internet age are nothing without databases. Then we talked about data, that's the metadata era, and that was important about 10, 15 years ago, still important. And now we're in the era of data science, and data science because it uses machine learning, is able to deal with unstructured data, which is what you find in flat files. So we come full circle, just like Shakespeare's 7 Ages of Man, my 7 Ages of data have taken us full circle. Now, I hope you found some of that sort of useful and interesting leaping off points. My first lecture was about algorithms, and my second lecture was about data. And that's because there's this famous book by Niklas Wirth, who is a Swiss computer scientist. Wirth is a hilarious person. He's full of interesting quotes about things, has very firm views on how you should construct programs. And his book, famous book, is called Algorithms Plus Data Structures Equals Programs. And so that's a cue for my next lecture, which will be about programs. And I think I'm going to take a sort of human-centered view to this. What is programming like? What does it do to people? What decisions do they make? And it's highly controversial because for every programming language that I like, there'll be someone else who thinks it's an abomination. Wirth is famous for the quote, C++ is an insult to the human brain. C++ is a programming language amongst many, and that's what I'm going to talk about next year. Thank you.